Okay. Welcome to the quarantine special series of STOC. We are excited to have Chi-Ning Chou with us to speak on optimal streaming approximation for all Boolean 2CSP. Chi-Ning is currently a PhD student at Harvard University working with Bose Barar. And yeah, so I guess without further ado, I'll just hand over the screen to Chi-Ning and let him begin with the talk.
Okay,
Right.
thank
Yeah.
you. Yeah, thanks for the invitation. It's my pleasure to share my recent work here. Okay, so maybe let me first share my screen. Oh, maybe you have to allow me share my screen.
Oh,
thank you.
I think we can share, right? You are already permitted to share.
It's really.
Oh, okay.
Oh, okay, I can share now. Okay, let's go to. Okay, nice. Okay, so can you see my screen?
Yes, I can see your screen.
So it's the 4-4-4-1. Okay. Okay, good. Okay, so today.
Okay, I think there is some issue with this. I can see two slides simultaneously.
Oh, okay. So probably it's the wrong one. Let me see. Okay, probably this.
Perfect. Yeah, great.
Okay, great. Okay. So, okay. Hi, everyone. Today I'm going to talk about recent work on the streaming approximation of a Boolean Max-2CSP problem. Okay, and this is a joint work with Sasha and Santoshini, and they are both from Harvard. Okay, so let me start with some motivation and a spoiler of our results, and then I'll start with formal definitions and the techniques. Okay, so the goal today is studying the Constraint Satisfaction Problem, which is abbreviated CSP. Specifically, we're studying the streaming model. And why we care about CSP actually, because CSP is one of the central computational problems in complexity theory. Lots of the combinatorial problems can be encoded as CSP. So like studying the property of CSP is like a central problem to understand. Especially in a streaming model, we can hope to prove some unconditional hardness about CSP. So in the usual case, as what we saw everywhere in complexity theory, usually if we want to prove some hardness of a computational problem, we are only able to prove conditional hardness by reduced from some NP-hard problem. But if we are restricted ourselves in the streaming model, then we are able to hope to get some unconditional hardness, which is a very rare things we can usually get. Yeah, so the combination of these two is like the focus of this talk. Yeah, and one specific motivation is this example. So now imagine that we want to solve this Max-DICUT problem in a streaming model where I give you directed edges one by one. Yeah, and now so you have so the edge is supported on n vertices, and maybe you have poly n number of edges. But now I only give you a logn space. Yeah, maybe polylogn space. So you cannot store the whole graph, but I still want to ask you what's the max size of the directed cut. Meaning that you divided the graph into two parts, the ingoing part and outgoing part, and I want to count how many edges follow this direction. And I want you to just give me an approximation. Okay, and by some trivial algorithm, actually you can get 1/4 approximation, and by further improvement, there's this 2/5 approximation. But on the hardness side, there's only 1/2 hardness, the impossibility result. So actually there's a gap between what's known and what's known in the algorithmic side and what's known in the hardness side. So this is like one of the motivation starting point of our problem. So we studied this very special case. So for this very special case of 2CSP, people don't know what's the optimal approximation ratio in the streaming model. Yeah, and actually one of the result of this work is showing that, oh, actually both this upper bound, this algorithm, and hardness is not tight. Actually, one can achieve 4 vial approximation, and this is the optimal. This is the best you can achieve using logarithmic space. Okay, so before I explain all the details, I'll first, oh yeah, and we can, and after this result, we can further show all the Boolean 2CSP. Okay, and for now, I haven't defined what's a CSP and what's the streaming model. I'll define soon before I explain all the proofs. And then I'll explain algorithm and hardness, and if I have time, I'll explain all the stuffs. So everything here is not too complicated, and hopefully everyone can learn something here. Okay, so good. So now let me start with some definitions on the models and the problems. Okay, and yeah, please feel free to stop me if anything is unclear. Okay, so CSP. So in CSP, there's two things. The first thing is variables. So we have x1 and xn, two xn variables, and they are taking value in this alphabet set sigma. So in a Boolean setting, when I say Boolean CSP, it means that the variable takes values like in 0 and 1. Okay, so it's a Boolean variable, and there are constraints. So the constraint is some functions on the variables, and this is also Boolean constraint. So for example, an and is a constraint. Yes, and so when I want to write down the constraint x3 and x8, formally I write it in this way. Yeah, so I specify a function, a predicate f, which is the end function, and I specify a subset, which is what this function is going to, this predicate is going to apply on. So with these two things, I can specify a constraint. Okay, and when I say 2 CSP, the 2 means that the predicate has arity 2. Yeah, sometimes people also say it's the width or the length of the constraint. Okay. Okay, so the inputs of the constraint satisfaction problem is then a bunch of constraints over these variables, and we denote the number of constraints as m. And the standard question here is then to ask you what's the number of the the maximum number of simultaneous satisfiable constraints. Okay, so that's why sometimes we add max in front of the CSP problem. So when we said this is a max CSP problem, it's like given you a bunch of constraints, I want you to tell me what's the largest number of simultaneously satisfiable constraints. Okay, and this is like formally how you write down the definition of the largest number of simultaneously satisfied constraint, and we denote it as the value of the input C. Okay, and as an example, we can actually encode Max-DICUT. So here is the undirected version of what I mentioned before. We can encode Max-DICUT as a CSP easily using XOR predicate as follow. So the Max-DICUT problem originally is like giving you an undirected graph. You have vertices and edges, and you want to find a cut, meaning that divided the vertex into two parts and maximize the cross edges. Okay, so how to encode this as the CSP problem? Maybe you can first think this for a while. Okay, so it's then hard to see that actually you can encode in this way. So if we associate each vertex with a variable, yeah, and the variable is set to 1 if and only if I include it into the set T. So if it is 0, then we think it is as another set. Yeah. So then when will an edge being a cross edge? This edge will be a cross edge if and only if the variable on two sides are set assigned to 0 and 1. Yeah. Meaning that, or another way to say that is like their XOR is 1. Okay. So given you undirected graph G, yeah, I turn every edge ij into a Boolean constraint, XOR constraint, XI, XOR XJ. Yeah, so this is exactly a CSP instance, and the value of this this instance will be the max-cut value.
So in this particular, yeah, so I have a question. So in this particular setting, you're putting F to be the XOR, right?
Yes, yes.
Okay.
Yeah, and S will be the I and J. Yeah.
Okay.
Yeah. Good. Okay. So in general, this is not a special case. Actually, CSP can be used to encode lots of combinatorial problems. It's not only about max-cut, and sometimes CSP can be easy. Sometimes are hard. For example, max-cut, actually we know that max-cut is NP hard. So then as a corollary, we know that to exactly know what's the value of the max XOR problem, this is also NP hard. But when it is hard or easy, actually there's a very nice theorem. It's called the Schaeffer theorem. It says that actually there's a dichotomy in a Boolean CSP when you talk about solving it exactly. Yeah, this Schaeffer dichotomy theorem shows that for every Boolean CSP problem, here I mean when you specify some type of predicates, yeah, you restrict F to be certain functions. You define a class of CSP problem. The Schaeffer's dichotomy theorem tells you that this problem is either P or it is NP hard. Yeah, there's nothing in the middle. Yeah, so in the exact version, this is basically solved in a very strong sense. Yeah, but in real life, because most of the problem it is, I mean, like max-cut is NP hard, so people sometimes relax it to the approximation version. So then it's a very natural to ask, what about in the approximation region? Do we have a full understanding on the approximating CSP problem? Okay. Yeah, but here then we have to formally define what do we mean by solving approximating, because exactly just output the exact value, but what do we mean by solving CSP problem approximately? Okay, so here we define the approximation by distinguish instances with different values. Okay, meaning that if you can, so actually there are various ways to view it, and this way I find it convenient, and so I'm going to define this way. So when I say there's an algorithm that gives alpha approximation to a CSP problem for some alpha between 0 and 1, it means that this algorithm can distinguish the following two cases. Yeah, the yes case is like when the value is greater than V, yeah, for any V. For any V, if the yes instance is greater than V, yeah, and the no instance is like the value is less than alpha times V. So this is a gap problem. Yeah, so I define alpha approximation in this sense. Yeah, okay, because I want to phrase it in a decision problem, so to avoid you require the algorithm to output some value. Okay, but it's natural and easy to transfer between two different definitions. But now here I phrase it in the distinguished problem. Okay, and then using this definition, one can actually see that when alpha equals to 1, this corresponding to the exact problem. Yeah. Okay. So we know that when alpha is 1, by the Schaeffer's dichotomy theorem, we know that this one approximation is either in P or it is NP hard. Okay, but what about for other value of alpha? One other natural setting people care about is this alpha equals to 1 minus epsilon for any epsilon constant greater than 1. Yeah, if this is in P, then people say, oh, this problem has a Fourier approximation scheme. Yeah, and if it's not, then it's not. Yeah, yeah. But in other setting, we might care about what's the best alpha we can achieve for certain CSP problem. Okay, and given this direction, then we can study the algorithmic side and the hardness sides to see what we can do. Yeah, and in the algorithmic sides, what people know is to do some random sampling, which I will mention later, And for a more fancy technique, it's called the STP-based algorithm, which I won't stress here. This actually cannot be implemented in a streaming model. Yeah, and on the hardness side, the standard result people know is to prove some NP hardness and UG hardness. Yeah, so NP hardness is like what I mentioned, like for the exact version. So for the when alpha equal to 1, people exactly know it is either NP hard or you have a polytime algorithm. But for the approximating region, actually is less clear. For example, for the Max-DICUT problem, we know that there's a trivial 1/2 approximation. And using SDP-based algorithm, you can improve this ratio to 0.878. However, for the NP hardness, the best NP hardness people know is only 0.941. So this is like a landscape is not that clear because we don't have a tight characterization about the hardness and the easiness. Yeah, but one very important contribution, one important exciting sub-area here is about the unique game conjecture. So for people who know this, it's a unique game is like some kind of problems. Yeah, if we assume this problem is hard, yeah, we want to do reduction to show other problem is also hard. And turns out that if you start from unique game, you can show that Max-DICUT is the 0.878 is the optimal one, but we don't know NP hardness. Yeah, so I guess my message here is that so about approximating CSP, there are many fascinating problems, and lots of the result is in a polynomial time regime is still open. Yeah, and many things can be characterized by unique game, but also the hardness of unique game itself is still remain widely open. Yeah, but today we are actually not talking about the polytime regime. We are care about the streaming regime, and this gives us some hope about the unconditional hardness. Yeah, so previously I just give you a big picture on what we know about the approximation CSP. And right now, starting from now, I'm going to restrict ourselves to focus on the streaming model. And this is because in the streaming model, we can hope to get some unconditional hardness. And the hope to here is like we are able to prove some more unifying and general theorems here. Okay, so it's so far clear. Okay. Good. So, okay. So now after defining this, the definition of approximating CSP and some motivation, let me start from some. Let me go to the streaming model. Okay. So actually, we already see the streaming model in the very beginning, but still, let me formally define it. So when we talk about CSP in a streaming model, we're saying that each constraint, receives in a string. Yeah, so maybe you have poly many constraints, but I receive one by one. So now you have an algorithm, and I give you a constraint one by one. And this algorithm might only have a sublinear space or even just logarithmic space. And the goal is to have approximations about the maximum number of satisfied constraints. Yeah. And similarly, if we have an alpha approximation, it means that the output V is at least the alpha times the optimal value. Okay, and a simple observation here is that because you cannot store the forward assignment because the forward assignment actually requires your own space. So here we only require to output the estimate of the value instead of generating an assignment, because for this streaming algorithm you even cannot store an assignment because storing assignment requires linear space. But here I only allow you to have a sublinear or even logarithmic space. Okay, so to let people have more feeling about the definition, maybe let's go back to Max-DICUT and look at this as an example. So for Max-DICUT, there's actually a trivial algorithm that gives you 1/2 approximation. And how can you do that? So now in a streaming model, we have a log space machine, and you receive age one by one. And actually, I claim that this simple algorithm already works. So the streaming algorithm just count how many ages he received, and then Here I'll put the number of edges divided by 2. Okay, and first observe that this algorithm can be implemented in logarithmic space, because now I just care about counting the number of edges, right? And if the number of edges is poly n, I only need a big O log n bits to record the number of edges. Yeah, so this is a log space streaming algorithm. But what about the correctness? Yeah, why output the number of edges divided by 2 already give you a helpful approximation. Yeah, this actually can be seen by an analysis using random sampling. So now imagine that I now randomly samples an assignment and calculates its expected value. Yeah, so meaning that I want to see a random cut. For a random cut, how many edges is a cut edges? Okay, and by the linearity of expectation, actually you can see that for a random cut, the expected number of cuts, size of the cut is the number of edges divided by 2. Yeah, so actually this means that the random cut value is the m divided by 2, then this means that there exists a cut having value this. Yeah, so this means that when you output the number of edges divided by 2, you are very sure by the analysis, you know that there exists this cut having this value. Yeah, but you don't know what this cut is, but you know there exists cut. So this is a trick here. Okay, so now using this simple way by counting the number of edges and output it divided by 2, we get a streaming algorithm with logarithmic space that give helpful approximation to max cut. Okay, and turns out that interestingly, this trivial random sampling algorithm for max cut actually is optimal in a very strong sense. So so people can actually show that for any constant epsilon, half plus epsilon approximation streaming algorithm for max cut requires omega in space. This is a very interesting result, culminating as a last year STOC paper by Kapralov-Krachun. They show that you need omega in space. Originally, it's shown by some other people like Kapralov, Cannon, Sudan. They first show that you need root n space, and they then further have some improvement. And last year, this paper can show that you need omega n space to achieve that. Yeah, so there's like an exponential separation between the number of the space needed to give a good approximation. Okay, and as a side note, you can actually note that, as I mentioned before, actually in the polynomial time regime, there's a SDP-based Goldman-Williams algorithm give you 0.878 approximation. So basically, this result can also be interpreted as the SDP algorithm cannot be implemented in sublinear space. Okay, so now for max cut is fully understand, but what about other Boolean CSP or even other Boolean 2CSP? For example, a very natural question is about Max-DICUT. So similarly, you can use a similar random sampling algorithm. You can see that now random edges is a cut with probability 1/4. So trivial random sampling, yeah, by streaming algorithm recording the number of edges and output it divided by 4, you already got a quarter approximation. But is this optimal? Yeah. So from the hardness side, if we using the hardness from Max-DICUT, the undirected version, you can actually get 1/2 plus epsilon hardness for free. But this is the best known before. And so there's a huge gap between 1/2 and 1/4. And interestingly, in this paper by Guruswami-Velingker-Velusamy, they show that actually you can do something slightly non-trivial. Yeah, actually we know 1/4 is a wrong answer. You can improve to 2/5, 2/5. Yeah, so this is like the situation. But then there's still a gap there. So what would be a right approximation ratio? And what about the other CSP? So this is the questions we are going to study.
So this
And
so this 2 by 5 approximation. What about the space over here? We are still talking about order of logn here in the algorithmic sense.
yes.
So
Exactly. Yes, good question. So this algorithm also can be implemented in big O login space. Yeah. Actually, all the known algorithm about this stuff, all the non-trivial algorithm can be implemented in login space. Yeah. So actually, we don't know how to say like n to the 0.1 space. Yeah, we actually don't know how to use those much space. Yeah. Either it is very hard, or yeah, we can directly prove it hard, or the algorithm just use login space. Yeah.
thanks.
Yeah. Okay. Yeah. So now this can goes to our results. So our first result is showing that actually the answer for Max-DICUT is 4/9. Yeah, we designed algorithm also in big O login space. You can already get 4/9 approximation to a Max-DICUT problem, and we also prove hardness. And then we further characterize all the approximation for all the other Boolean 2CSP problems. Yeah, and this can be summarized in this theorem. Yeah, it's like so now I only list 4 types of Boolean 2CSP, and I claim that for the other, you can reduce to these 4 types. Yeah, so you can actually see that for the OR Max-2O problem, the type. So this alpha is the optimal approximation ratio. Yeah, and we can show that for type lambda, yeah, you always have alpha minus epsilon approximation in log space. Yeah, but for alpha plus epsilon approximation, you require polynomial space. Yeah. Basically, everyone needs at least a root n space. Okay, and you can see that actually the approximation ratio for Max-2O also is weird. It's √2 divided by 2. It's something around 0.7. It's not by the trivial random sampling algorithm. Okay, so now, so in the rest of my talk, I'm going to briefly mention about the algorithmic ideas, and also mention about the reduction idea, the hardness idea, and then I'll sum up with some open problems and future directions. Okay, so for now, is there any questions about the problem setting and the results?
Yeah, I think it's fine. Yeah.
Okay, so if it's clear, then I'm going to go to the algorithmic side. Okay, specifically, so we have several algorithms need to prove, but let me focus on Max-DICUT, and for the other similar ideas. Okay, so as a warm-up, maybe let's first take a look at what's this 2/5 approximation algorithm by Guruswami et al. Yeah, so recall that what's known before then is a trivial 1/4 approximation and a 1/2 hardness approximation. Yeah, and their first idea, their key idea, is to consider the bias of each vertex in the directed graph. Yeah, and they define the bias in the following way. So for vertex V, because now we are working on directed graph, we define the bias of the vertex V as the in degree minus out degree. Okay, and then so this definition basically give us a vector where the entry encodes the bias of the corresponding vertex. So if you have n vertex, then you have an n-dimensional vector, the bias vector. Okay, and and then they define the total bias to be the sum of the absolute value of the single bias of each vertex. Okay, so if you think about the vector view I mentioned to you, the total bias basically is the L1 norm of the bias vector. Okay, and interestingly, using some seminal results in the streaming algorithm community, we know that for a vector, where this vector, the value is updated by the input you receive, yeah, you actually can approximate the L1 norm of this vector in logarithmic space. Okay, so here I won't talk too much about details because this requires some other knowledge in the streaming algorithm sides. But maybe you can take this as yeah, it is known, it's folklore. Yeah, we know that yeah, if you just want to, people call it sketch. If you just want to sketch the L1 norm of a vector, yeah, this vector is updated by your input in some way, then you can do it in log space. Meaning that in this context, it means that for total bias, you actually can approximate total bias using log space. Yeah, so this satisfies our constraint. We want to have a log space algorithm.
And
okay.
how good is this estimation? Estimation of
Oh yeah, so good question. So here we are talking about multiplicative approximation. So it's a 1 plus minus epsilon approximation, and this can be, so if you have 1 plus minus epsilon approximation, you can do it in 1 over epsilon squared logn space. Yeah. So if you think of epsilon as constant, then it's fine. Here epsilon should be think of as constant. So the constants.
Sorry, for all epsilon, right?
Yes, for all epsilon.
For all epsilon, 1 plus minus epsilon.
Yeah. Oh no. It's like fixed and epsilon.
Or
yeah.
Fixed. Okay. Sorry.
Yeah, and yeah, for fixed epsilon, and I give you 1 over epsilon square logn space, you can achieve 1 plus minus epsilon approximation. Yes. Yeah. Good clarification. Yeah. Okay, so this means that we can actually have an approximation of this bias, total bias in log space. Okay, then if you can understand what's the relation of bias and the optimal value, then basically I claim that you can already improve and get some good approximation ratio. Yeah, because like previously, the trivial algorithm I mentioned, just you count the number of edges. So it's like you count certain parameters of the instance. And by this bias definition by Guruswami et al., they basically show there's another quantity called total bias, which is useful, and you can understand this quantity in log space. Okay, so basically this is what they show. They can partially characterize what's the relation between the optimal value and the total bias, and I represent it in this figure. So first, they can show that actually there's an upper bound of the cut value induced by total bias. Okay, so specifically, for example, when the total bias is 0, meaning that each vertex, the in degree equals to out degree, yeah, they can actually show that the optimal die-cut value is at most half of the number of edges. Yeah, and this actually is intuitive, right? Because if you have a cut edge, the other side definitely is not an edge. Yeah, because now now the in degree equals to out degree. Okay, but not only for total bias equals to 0, they can characterize the whole range of B. Yeah, they can show that there's an upper bound. Yeah. In the meantime, they also show a lower bound. Yeah, which I represent in this red line. They show that given you certain bias, the value is at least above this line. Yeah. So meaning that so any directed graph, the relation between total bias and the optimal value must lie between this blue line and red line. Yeah. And I claim that actually once you have this figure, actually you already have a new streaming algorithm approximate Max-DICUT. And this algorithm just simply output the red line. Yeah. Okay. So if you recall, the requirement of the approximation algorithm is just giving you some value with the guarantee that the optimal value should be at least this value. Yeah. Yeah. You just want, I just want you to output something where you can prove that there must exist a DICUT having this value. Yeah. So because they can prove this red line, they said every graph, their optimum value lies above this red line. So if I just compute the total bias and output the corresponding red line value, then I know that there must exist this cut. So outputting red line is a valid streaming algorithm for approximate Max-DICUT.
So I am a little curious at seeing this graph. So the red line over here goes like straight for some time and then takes this linear fashion. Yeah. So is there some intuition behind why this is happening? Like what does it?
Yeah. So basically they use two ideas to prove lower bound, and they take the max. Yeah. So one lower bound is this m/4, which is the horizontal line. Okay. Yeah, and another line is this this linear line, and they take the max of them. Yeah. So then it looks like this. Yeah. Yeah. For different region, they have different reason. Yeah. Okay. And is the algorithm clear? Yeah. How to? Yeah. So the algorithm just approximate total bias and output red line. Yeah. And then how to analyze the ratio? Actually, then you just analyze what's the maximal ratio between the blue line and the red line. Yeah, and this is actually exactly this 2/5. Okay, so this is their algorithm. Okay, so what's our new idea given this? So basically our observation is like, okay, if you believe this algorithm is tight, then you must be able to construct some instance that match both the, you can construct some instant match the blue line and construct some other instant match the red line. But then we realize, oh, actually we don't know how to do that. And then we realize actually red line is not tight, so we can improve it. And then we can further improve the approximation ratio. Okay, and how, so how do we realize the red line is not tight? Is that we discover some new way to argue the existence of a DICUT. Okay, and this idea is by random sampling. Okay, so let me define it. Yeah, and it's like using bias. Yeah, because now actually you have bias. Okay, so yeah, so maybe I'll skip this. Yeah. Okay, yeah, I can. Yeah, because I don't have too much time, so I'll skip some intuition and directly tell you about what's the algorithm. Okay, so now imagine that for each vertex I, yeah, you know its bias. Yeah, and then intuitively, if this vertex the in degree is greater than the out degree, yeah, then you would tend to set it as the in degree set. Yeah, you want to put it in the in degree set. Yeah, and if the bias is negative, means that the out degree is larger than in degree, you want to put in the out degree set. Yeah, because in the end, we want to count how many edges go from the in degree set to the out degree set. Yeah, but now instead of directly putting it into the in degree set, we give it some weight. We give it a probability delta. Yeah, to decide, we randomly sample, we randomly decide whether to assign I to the in degree set with certain probability. Okay, so formally for I, we send it to ingoing set with probability half plus delta times the sign of the bias. Okay, so the sign of the bias is +1 if in degree greater than out degree. Yeah, and it is a negative one if the other way. So basically, here is saying that if the in degree is greater than out degree, then I set it to ingoing set with probability half plus delta. Yeah, and otherwise I set it with half minus delta probability. Okay, and this might look confusing, so let's instantiate delta to have some feeling. So when delta equals to 0, meaning that actually there's no bias, we assign each vertex with equal probability to both sets, then actually this is a trivial random sampling, right? Because I assign the value with the equal probability. And this gives you 1/4 approximation. Okay, and what's the other extreme? The other extreme is to set delta to be 1/2. So this is called a greedy algorithm, because you basically when the in degree is greater than out degree, then you send it to the ingoing set, and if the other way, you send to the outgoing set. And this is exactly done by the Guruswami et al.'s paper. Yeah. So in these two extremes, one is the trivial random sampling, and the other is greedy algorithm. And basically, our idea is like, why not set it in the middle and optimize it? Maybe you can get a better approximation ratio. Okay, and actually this is the case. By not setting delta to be 0 or 1/2, you can actually get a better relation between the optimal value and bias. Yeah, so we can get this new lower bound rather than the one get by GVV17. And this looks not so intuitive, but so let's plot it on the previous figure. So this is what we know before. And basically our lower bound just slightly improved the red line a little bit. Yeah, by this weird curve. Yeah, we show that when the bias is small, actually the previous lower bound on the optimal value using total bias is not tight. We have this new green line. Yeah, so then our algorithm just becomes estimated B and output the max of green line and red line. And then the approximation ratio will be the maximum difference, the maximum ratio between the blue line and the max of red and green line. And with some calculation, you can show that, oh, this is 4/9. Yeah. So far we have improved the approximation algorithm by GVV using greedy analysis. Actually, the algorithm basically roughly the same. You approximate bias and output something, but we improve the analysis. Okay, by an observation that you actually can do sampling with some bias. Okay, so is the algorithm here clear? Okay, good. Yeah, so using similar idea, we can improve the algorithm, the trivial algorithm of Max-2 but due to time limit, I won't explain here. And yeah, if you're interested in details, you can either go to our paper or ask me offline. Okay, and in the rest of the time, I want to use maybe 10 minutes to tell you some insights about the hardness, and then summarize with some open problems. Okay, so good. So the hardness side. So basically now we want to show that in the streaming models, you cannot achieve certain approximation ratio using using a small space, like sub-root n space. Okay, and the one punchline is like the idea is to find instances that match the random sampling bound we have shown. Okay. Okay, so in general, how to prove streaming lower bound? As I spoiled in the very beginning, the one motivation to study streaming model is that you have a hope to prove unconditional lower bound. So what's the intuition of this? Yeah, the intuition is that actually in streaming model, you can relate lower bound problem to communication gain, communication complexity. Yeah, and the high level idea is like this. So the high level idea is like, there's a general framework to turn a streaming algorithms into a communication protocol. yeah, in a way that Alice and Bob, they do something to the streaming algorithm, and then sends the configuration of the streaming algorithm to the other person. And the other person then inserts something to the streaming algorithm, and then sends the configuration back. Okay, so in the communication complexity, the complexity is measured by the number of bits communicated. Yeah, maybe the max of each rung. Yeah, so then you can notice that actually the space used by the streaming algorithm is then like an upper bound of the communication complexity. Okay, and in the communication complexity community, they are able to prove some lower bounds on the communication complexity of certain problems. So then this further give you lower bounds on the space used by streaming algorithm. Yeah, so this is a high-level intuition, because using some tricks, yeah, it depends on the problems. You can design protocol using streaming algorithm, where the number of bits transmitted is just the space used by streaming algorithm. So if you have communication lower bound, then you have streaming space lower bound. Okay, so here now for us, then we are then just interested in identifying the right communication problem, and then try to design a protocol for this problem using streaming algorithm. Okay, and this specific problem actually is not discovered by us. It's like used by the previous Max-DICUT hardness people. Yeah, this communication problem called distributional Boolean hidden partition problem is then the key communication problem we are looking at. Yeah. So yeah, so let me directly define the communication problem, and then let's see how to use it. Yeah, in terms of proving hardness of CSP, approximating CSP. Okay, and so this is a two-party game. You have Alice and Bob, two-party, one direction game. So for Alice has a hidden partition, which is also hinted in the name of this problem. And this partition is encoded by an n bits vector, 0, 1 to the n. I denote that x star. Okay, and for Bob possesses of two things. So the first thing is this m. M is a matrix of size 0.1 n times n. So you should think of each row of m as encoding an h, or yeah, of a matching. Okay, so this m actually encodes a matching of size 0.1 n. Yeah, and we encode this matching like in the row of this matrix m, so that each row of n has exactly to 1. Yeah, encode the corresponding vertex. Okay, and this w will be specified in a way I'll explain later. Yeah, and the goal is to decide. So then, after receive some message from Alice, C bits of message from Alice, Bob has to decide whether this is a yes instant or no instant. Defined as follow. So the W vector Bob receive, if it is a yes instance, then this W actually equals to MT times X star. Okay, so this is like the structural case. So there's some relation between Alice's inputs and Bob's input. However, in a no case, W just a random, uniformly random vector. Okay, so in this communication game, the goal is to Alice transmitting some message to Bob, and then Bob has to realize, whether the input he received is from yes distribution or the no distribution. Okay, so is this setting clear? Okay, and interestingly, so if you think a little bit more, but I probably won't explain this by some pigeonhole sort of first step paradox. Yeah, you can show that root n, when Alice sends root n bits, yeah, it's enough. And then this seminal work of Gavinsky et al., they show that actually root n, the trivial protocol is tight. Actually, any protocol that so that Bob can achieve can succeed with non-trivial probability, say 2/3 probability, requires omega root communication. Okay, so if we put back into the context before, it's like now we have a communication gain, which we know there's we have a lower bounds on the number of bits used in the protocol. Okay, and this game is this very specific form. Yeah, Alice has a hidden partition, and Bob has a matching and a special vector, and he wants to decide these two cases. Okay, and one small tricks here, which I won't elaborate, is like actually in a real reduction, we actually need a capital T many copies of Bob, and these things we call it parallel repetition. This is also standard techniques. Yeah, in order to we want to have actually more matchings, but this is tricks I won't mention here. If you are interested, I can talk offline. But I hope this don't be bothered by this for now. Yeah, but I mean, later on we will imagine we have many copy of Bobs. Yeah, at the same time. Yeah, but don't be confused by this. Okay.
Yeah, sure. Just one question: that these copies of Bob, will they be communicating among themselves, or they'll be independent? They'll only be communicating with Alice.
Oh yeah, very good questions. Yeah, so they won't communicate with each other. Yeah. So yeah, intuitively this is like how to say? Actually, yeah, actually the real way we did is Alice send something to Bob 1, Bob 1 send something to Bob 2, and then go on. Yeah, and then but yeah.
Okay.
In the end, we will reduce this problem back to only one Bob case. Yeah.
Okay.
So by fixing something of the previous Bob or something like this. Yeah. By doing some hybrid argument. Yeah. I can explain more offline,
Sure.
but this is not the key. Yeah, key point here. Okay.
Sure.
Good. Okay. Nice. Good questions. Yeah. So now, to have some feeling why this communication problem is useful, let us use this to prove lower bound for Max-DICUT. Yeah, so this is an example. Yeah, and yeah, maybe we'll use it in the Max-DICUT, so I won't explain the slides. Okay, so for Max-DICUT, okay, so now suppose we have 3 Bobs. Yeah, we have this. So for Bob 1, you have this W1 vector, and M encodes a matching. Yeah, you can see that actually now here is not matching because a vertex have more than one edges, but just illustrate here. Okay, so how to reduce this to Max-DICUT? So basically recall that, so now we want to use a streaming algorithm to solve these communication gains. Okay, so now we imagine we have a streaming algorithm that approximate Max-DICUT. Yeah, and we want to design a protocol for this distributional Boolean hidden matching problem, hidden partition problem. Okay, so imagine you have a streaming algorithm for approximating Max-DICUT. So for Bob, he will insert each edges into the streaming algorithm according to this W vector. Okay, so if the W vector has a 1 in one entry, then we insert the corresponding row, the edge encoded by the corresponding row to the streaming algorithm. Yeah, for example, for Bob 1, only the first entry is 1, so Bob inserts the first row, which corresponds to edge 2, 3 to the streaming algorithm. Okay, and similarly for Bob 2, he inserts the first and the third edges to a streaming algorithm. And similar for Bob 3. Yep. And then, so now the Bob 3 have the configuration of the streaming algorithm inserted with so many edges. So then he will ask the streaming algorithm to output certain value. And then using this value, he will decide whether this is a yes case or no case. Okay, and then you will actually notice that the yes case of the communication problems actually will corresponding to the case where there exists a cut for this cut actually is encoded by the X star by Alice. Yeah, there is a max cut satisfied that cut all the edges. Yeah. And by some concentration argument, you can show that in the no case, actually any cut is at most half plus epsilon times n with high probability. Okay, so this means that the protocol I described can solve this problem, can solve the DBHP problem. Meaning that if you have a half approximation algorithm for the max cut, then you can use this, the reduction I explained here, to design a protocol to solve DBHP with good probability. Okay, nice. So actually this is known before, but then we want to use this similar idea to prove hardness for the other problems we're interested in. Yeah, but before that, maybe let me give a more unifying view on this communication problem and how to use it to prove hardness in the streaming model. So actually, you can have a graphical view on this DBHP problem. So now, recall that Bob have two things, right? You have MT and WT vector. And you can think of this as you use WT to pick MT, as we discussed before. So now for the yes distribution and the no distribution, then it looks like this. So recall that in the yes distribution, there is X star such that WT equals to MT times X star. So then if you use WT to pick the edge of MT, then how will it looks like? It will actually looks like this. Yeah, this becomes a bipartite graph. Yeah, because you only pick the edges when WT is 1, and it happens if and only if one of the vertex lies outside the X star and the other lies inside X star. Okay, and for no distribution, since WT is uniformly random, basically what you get is a random graph. Okay. And now you can think of that each player, each Bob, yeah, they actually possess some subset of the edges here. Yeah, so in a yes distribution, each Bob possess some edges in this hidden bipartite graph. And in the no case, each of them just contain some random edges. Okay. And for convenient here, I define another distribution, which I call yes prime distribution. Yeah, which is defined by 1 minus the mx star. So basically doing negation. So now the graph looks like this. Yeah, and think of each Bob possess some subgraph here too. Okay, good. So using this view, we can then easily reprove the max cut hardness again by thinking of Bob having the edges assigned indicated by W. So then the max cut reduction, just then you send IJ those edges directly to streaming algorithm and then output it. Yeah, and for yes distribution, the graph streaming algorithm C is exactly on the left, and if it is no distribution, it's on the right. Yeah, this is the graph, the streaming algorithm C. Yeah, so then you can know that if the streaming algorithm have good approximation, then Bob can distinguish these two cases. Okay, so now I just rephrase the problem, but this will be helpful when we are looking at the other reductions. Okay, so yeah, so since due to time limit, maybe I will directly jump to the reduction for max directed cut. Yeah, and also, by the way, Max-DICUT basically is max to end. Yeah, the constraint is end. Yeah, and the other reduction, you can talk to me or yeah, read our paper. Okay, sounds good. Cool. Yeah, so let me directly go to Max-DICUT. Okay, good. Oops, I jumped too much. Okay, Yeah, so recall that. So now recall that. So from a graphical view, we know that each bob now has some edges. Yeah, from a graph generated either from a yes distribution or the no distribution. Yeah, and in this reduction from DBHP to Max-DICUT, we have one more trick. Yeah, we actually also let Alice to send something to the streaming algorithm. And recall that this is valid because actually all the communication is starting from Alice, so this is fine. You can prove this is fine. Yeah, and because Alice has the knowledge of X star, so actually Alice now can do something bad. Yeah, not something bad, actually it's good to us. Alice can do something that can be helpful to us. Yeah, so recall that for the Max-DICUT problem, if you recall what's the figure before, yeah, the worst instance, the worst ratio between the blue line and the green line, lower bound, upper bound of the bias value graph, is not happen when bias equals to 0. It happens when bias equal to something like maybe 0.4 or something. Yeah, so means that the bias is non-zero. Yeah, so we are going to use Alice, let Alice to generate some bias edges corresponding to the bias, yeah, and then send to the streaming algorithms. And then for each bob, actually, when there's an ij edge in bobs just sends an edge from j to I and an edge from I to j. Okay, so now I define reduction. We can see how is the distribution looks like. So this distribution is the distribution the streaming algorithm sees. Okay, so if the communication problem is generated from the yes instance, the streaming algorithm will see a directed graph on the left. Okay, so there are two graphs on the left. Yeah, the left one is generated by Bob collectively. Yeah, remember, because for Bob, you have ij edges. Yeah, and I turn the ij edges to directed edges from I to j and j to I. Yeah, and in a yes distribution, this ij corresponding to the cross edges. So then it looks like this. Okay. And for Alice like has this knowledge of X star. Yeah, the edges it sends to the streaming algorithms is going from one way. Yeah, so it looks like the second left graph. Okay, and for no distribution, so the only difference between no and yes distribution is Bob's edge. So in the no distribution, Bob's edge becomes random. Yeah. So then it just looks like this, becomes a random graph plus something. Yeah, and then we are able to show that, so the streaming algorithm received these two different distributions. And in our analysis, we can show that on the left, the value of this yes distribution directed graph is at least this stuff, this quantity. And on the left is this, at most, this quantity. Okay. So if the streaming algorithm can have a good approximation, then he can distinguish these distributions, and then he can distinguish the yes and no distribution to the communication problem. Okay, so the detail here is just do some calculation, but intuitively, it's like we want to use the different structure of the yes-no instance of the communication game to design the corresponding CSP instance, such that the yes instant and no instant has a gap between the value. Okay, and the rest just analysis. Okay, and for the other ones, it's also similar. Okay, and the way we design the gap instance then is inspired from like the bias algorithm. Okay, good. Okay, so yeah, hope I don't overwhelm people, but if you are interested in learning more details, you can talk to me or yeah, read the slides or the paper. Okay, good. Okay, so I'll skip the other lower bounds. This might be too much. Yeah, but the idea actually is still similar. Yeah, we want to reduce the yes instant, no instant from the, or here is yes prime instance from the communication game to the CSP instance. Okay, yeah, so this is summarized in this table. Yeah, so basically,
So
okay.
I have a question. I know you told everyone to not be bothered about the instances of Bob, but it is still very intriguing to know like what does this T parameter is. I mean, is it really depending on something from the Alice or something else? I mean, I don't know. Like why?
Oh, okay. Okay, so this T parameter actually only depends on, what to say, the success probability. Yeah.
Okay.
Yeah, so this is something, but success probability we think of it as constant. So you should think of T as a big constant. Yeah, it doesn't depend on N at all. Yeah. Yeah, that part is a little technical, but also standard. Yeah. Okay. But the takeaway you should have after this the hardness section is that in general, actually this techniques have been quite general. Yeah, you just have a communication gain. You have yes and no instance. Yeah, and then you reduce the yes no instance of the communication gain to yes no distribution of CSP instances, such that they have a huge gap on the optimal value. Yeah, and the gap, the ratio of these two instances will be the hardness of the ratio you can achieve. Okay, great. So let me conclude. Yeah, so basically what we did is to characterize all the optimal approximate ratio for Boolean 2CSP in the streaming model. Yeah, specifically we have these ratios. Yeah, and one high level message getting from here is like somehow all the algorithm can be achieved using either random sample, the trivial counting number of edges, or combining with bias. Yeah, so this is saying that in the streaming model, somehow magically, yeah, you just counting something locally and then use it to do random sampling, then this is optimal. Yeah, you don't need anything fancy like a SDP algorithm. Yeah, so in the streaming model, actually some local random sampling is optimal. Yeah. Okay, but of course, I explained some idea about the algorithm and hardness size, but there I skipped some details. For example, I didn't tell what's the reduction to arbitrary Boolean 2CSP. I only focus on specific one, but believe me, they are fine. Yeah, you can easily construct reduction between them. And I also skip the details of how to compute bias. Yeah, you require some knowledge in streaming algorithm to sketch the L1 norm of a vector. Yeah, I also skip this detail on the parallel repetition, like the mysterious many bobs. Yeah, it looks mysterious, but actually this is standard. Yeah, and for all these things, yeah, you can consult our paper or ask me. Yeah, but yeah, I want to list to make sure. Yeah, to be honest on what I missed. Okay. Okay, great. So finally, let me conclude with some future directions. So basically, this fields of studying the unconditional hardness of approximating CSP in the streaming model is still in quite early stage. You can see that before our work, there's only very few works on Max-DICUT and some other problems. And we capture, and in this work, we settled down all the Boolean 2CSP. But there are still some small complaint here. For example, that we only can prove omega root n space lower bound. Yeah, well, for Max-DICUT, people can prove omega n lower bound. So this will be a very interesting open problem, how to improve this. Yeah, but maybe we need new communication lower bounds to prove this unknown. Yeah, and the more midterm and very exciting direction is to show Max-2CSP for larger alphabet set. Yeah, so here we focus on Boolean. And a recent paper by Guruswami and Tao, they can generalize to a larger alphabet size, but they can only handle unique game constraints, meaning that the constraint only have exactly so for each setting of a variable there exists another setting, exactly one setting. Yeah, so it's not general for any constraints. Yeah, so it's still widely open. What's the optimal approximation ratio in the streaming model for 2 CSP with larger alphabet sets? And another similar question is to understand the Boolean Max-CSP with larger arity. So here we only have 2 variables in each predicates. What about larger one? This is also very intriguing questions. Yeah, and this is also studied in a standard model, but yeah, also widely open. And in long term, yeah, it will be interesting to see what's the optimal behavior in the streaming model about approximation CSP. Yeah, I mean, because in this work, we characterize everything about Boolean 2 CSP, but is this just an accident that somehow we can do for Boolean 2 CSP? Or can we hope to prove a more general theorem like the Schaeffer's dichotomy theorem in the streaming model? Yeah, it's unknown, and it's also very exciting because we know that in the polytime regime, this is believed to be hard and there's no unifying theorem. But in the streaming model, it's less explored, and somehow for 2 CSP case, we can characterize everything. This gives us some hope that maybe we can have a unifying theory here for every Max CSP. Yeah, but unknown. Okay. Yeah, so that's my talk, and thanks for everyone who watched this either online or here. Yeah, thanks so much, and let me know if you have any questions.
Thank you.
Okay.
Thank you so much.
Sure.
Yeah, just one message, one usual message to all the viewers. If you have any questions, doubts, you can post them in the comment section below. And yeah, we'll see if Chi-Ning can answer them in some time. And all the necessary links and details are also available in the YouTube description. And yeah, so all right, thank you so much, Chi-Ning. This was very interesting, a very nice talk, and yeah, looking forward
Thank you
to
too.
more results in this area. Yeah.
Thank
Cool.
you.
All
Okay.
right.